Welcome to the deep dive. Today we're jumping into a set of sources that explore something. Something that really bends the mind. We're talking about the absolute power of gravity, not the kind that keeps your coffee mug on the table, but as this universal tool that literally changes how we see everything. Our focus is on this really bizarre interaction between gravity and light. We're looking at notes explaining how huge objects actually warp the road that light travels on. Which is just, think about that. Light moves at nearly 300,000 kilometers a second. It's the universal speed limit. So you start with this paradox, right? If light is the fastest thing there is, what kind of force could possibly grab it and, change its direction? We're all taught light travels in a straight line.
And that paradox is exactly what makes this so fascinating. Our mission for this deep dive is to really get our heads around gravitational lensing. This isn't just some abstract idea. It's the surprising fact that the universe has its own built-in optical systems. It turns entire galaxies into these giant telescopes that we can use.
Okay, let's unpack that because I think the common idea is a little bit off.
Mm-hmm.
People might picture gravity as like a magnet sort of pulling the light beam sideways.
Mm-hmm.
But the sources make it clear that's not what's happening at all, is it?
Not at all. That's the fundamental misunderstanding. The light isn't being pulled. It's doing what light always does. It's trying to travel the shortest path possible. But, and this is the key, massive objects, like our sun or a whole galaxy cluster, they create a kind of dent in the fabric of space-time.
A dent, okay.
Yeah, a dent. So the light is still moving straight, but the path itself is now curved. The best analogy is to imagine a bowling ball on a big, stretched-out rubber sheet. It makes a dip.
Right.
Now, if you roll a little marble, that's our beam of light, past that dip, it has to follow the curve. It thinks it's going straight, but its whole environment has been bent.
And sources say it's not just space, but space-time. So time is part of this distortion, too.
Exactly, and that's where it gets really beautiful. Time actually slows down the closer you get to a massive object. So that path, that curve, is what's called a geodesic. It's the most efficient route through a warped spacetime. It's the universe's version of a straight line.
And that's where the abstract physics becomes a practical tool. If a huge object can bend space and redirect light, well, then it's acting just like a lens.
It is a lens, a cosmic magnifying glass.
So we can use it to zoom in on things.
We can. Gravitational lensing allows scientists to use a massive galaxy as a natural telescope to magnify light from, say, a much smaller, incredibly distant galaxy that's sitting right behind it.
But if the gravity is strong enough to bend the light, doesn't it also distort the image? Are we getting a clear picture?
That is a fantastic question, and the answer is it really depends on the alignment. It's not always a perfect image. Sometimes when the alignment is just right, you get what's called strong lensing, and that's where you see those incredible images.
The ones that look like something out of science fiction.
Yes. You see these giant, stretched-out arcs of light, or even a perfect circle called an Einstein ring. The image is magnified, but it's also, heavily distorted.
So you might see multiple copies of the same galaxy, or it's all smeared out.
Right, and astronomers have to use software to basically unstretch that light and figure out what the original galaxy actually looked like.
Wow, so it's like cosmic archaeology. You're piecing together the past from these warped clues.
That's a great way to put it. And then there's weak lensing.
Okay, what's that?
That's when the alignment isn't as perfect. The effect is much, much subtler. You don't see big arcs, just tiny, slight distortions in the shapes of background galaxies.
So why is that important?
It's monumental, because by measuring those tiny distortions over a huge patch of sky, we can map out where all the mass is. Specifically, we can map dark matter.
Because you can't see the dark matter itself, but you can see its gravity bending the light.
Exactly. We're seeing its gravitational shadow.
So with this cosmic zoom lens, what are we actually seeing that we couldn't see before? Why is it so essential?
Well, it's our best tool for seeing the very early universe. These distant galaxies, the first ones to form, are incredibly far away, so their light is unbelievably faint.
And stretched out by the expansion of the universe.
Right, so this natural lensing effect can boost their brightness by, a factor of 10, 20, even more. Without that boost, they'd just be invisible, even to our best telescopes.
So we're literally seeing things that would be impossible to see otherwise.
Impossible. The universe is doing the heavy lifting for us.
That's incredible. And it really brings us to the next point, which is just the sheer scale of this. If you need a whole galaxy to act as a lens to bend light, what does that tell us about the power of gravity out there compared to the, pretty gentle version we have here on Earth?
It tells us that what we experience is Almost nothing. It's a gentle hug, like you said, compared to the forces at play in the cosmos. To really appreciate it, you have to look at the most extreme examples in the sources.
Like near a black hole.
Exactly. Near a black hole, gravity is just turned up to the absolute maximum.
Mm.
The gravitational field is so incredibly steep that tidal forces become immense.
And tidal forces are the difference in the gravitational pull across an object, right?
Precisely. So let's say you were falling feet first toward a black hole. The pull on your feet would be so much stronger than the pull on your head.
I can't even imagine.
That difference, that tidal force, would start to stretch you.
Stretch you.
Yeah. The sources have a name for it. It's called spaghettification.
I'm kidding.
I'm not.
Yeah.
The gravitational gradient is so intense it would stretch you out, pulling you apart at an atomic level until you were long and thin like a strand of spaghetti.
That is
Mm-hmm.
a very effective and terrifying image. It really makes you appreciate the calm, gentle gravity we have here on Earth.
It really does.
Just the fact that we're not being actively deformed is something to be grateful for.
So let's bring this deep dive home. We started with this puzzle light speed versus gravity, and we've learned that gravity doesn't just hold us down, it redraws the map of space. It's a tool that turns galaxies into telescopes and lets us look back in time.
I think the biggest takeaway for you, the listener, is that the path light takes isn't some fixed, absolute thing. It's not a rigid line. Its route is totally dependent on the topography of the cosmos, bending and weaving around these massive objects in space-time.